Hello everyone, in this video we are going to be discussing the 2D aerodynamic analysis of a skydiver using CFD. This is by me, Adrian Espinoza, and my partner, Adrian Galvan. A quick outline before we get started. We will be discussing the CFD fundamentals and applications, then talk about the importance of CFD to then introduce our problem that we will be analyzing. We will discuss our methodology and our expected results. So CFD, or computational fluid dynamics, utilizes models created by the user to solve the flow of fluids and displays the results in the form of graphs, numerical methods, and /or animations. CFD is very widely used throughout multiple industries, and so it has many applications. It can be used in aerospace, automotive, power generation, chemical manufacturing, medical research, meteorology, and astrophysics. Here we have some examples of CFD in action. Here it can be seen in aerospace and automotive, where the velocity and pressure can be observed. Then it can also be used in weather forecasts, as you can see in the bottom left, and then bottom right, it can also be used in medical research, like for nasal passage and arteries.
So, CFD provides an alternative to real-world experiments by mimicking real-life conditions and simulates them through computational software such as ANSYS. The analysis provided by using CFD instead of experimental testing is much more accurate and provides a lot more data that would otherwise be difficult or impossible to obtain. CFD is also relatively cheaper than real-life experiments while being safer and much more time efficient than experimental testing.
So for our problem, we are going to analyze the aerodynamics of a skydiver at terminal velocity. And terminal velocity is basically the maximum velocity that a skydiver experiences. So when a skydiver jumps off a plane, it accelerates through the air until it reaches a terminal velocity, which is basically the maximum velocity. And we're going to observe the pressure and velocity contours of the diver at this velocity. And lastly, analyze the effects of the skydiver if he was to rotate through animations.
For our methodology, our skydiver's geometry is in a skydiving position you see on the right, with a length of 1.76 meters, a height of 0.7 meters, and we used a mesh domain of 50 meters by 25 meters. For the mesh specifics, our mesh element size is 0.5 meters. We used the triangles method, body sizing of 0.02 meters for the rotating body. The edge sizing was 0.01 meters for the skydiver and 0.02 meters for the circle. We also used a mesh refinement of 2. Continuing with the methodology for our solution setup, we used a transient unsteady flow with a K-epsilon viscous model with enhanced wall treatment. Our end-lift velocity was set to 53.6 meters per second, which is terminal velocity. Our residual monitors were set to 1 times 10 to the negative 6. We used standard error values, and we did second-order solution methods for the turbulent methods.
So we expect to display a uniform and elegant mesh through CFD, and also showcase the velocity and pressure contour animations. And we're expecting to see an increased amount of pressure in areas where the surface area is greater, as well as an increased velocity on the angled libs, for example, the arms and the legs. Alright, so now we're going to head on over to our workbench, to our fluid flow analysis. So first off, we're going to want to go into the geometry properties and make sure to select 2D, because this is going to be a 2D analysis. Then we can go on into our geometry. We were able to successfully solve this problem through CFD, and so now we are going to give you a quick rundown of all the steps we followed. First off, you want to start off with the sketch of the diver, which you can see here. Here you can see some of our dimensions for a diver with a total length of around 1.76 meters and a height of about 0.7 meters. Once the sketch was drawn, a surface was created from the sketch by using the option surfaces from sketches under concept. The surface was left as add material, which is very important since this is going to be the body that will rotate. Then we created a separate sketch number 2, where it's a circle around our rotating body. This was set as add frozen. Then we created a boolean from these two surfaces, where our target body was a circle and our tool body was a skydiver. After the boolean, a third sketch was done, and this is where a rectangle with a length of 50 meters and a height of 25 meters. And you also have to make sure to draw an additional circle on top of the previous circle, and this was also frozen. Then from our 2 parts and 2 bodies, we renamed our circular body to rotate and changed it to fluid. Then we renamed the rectangular body to fluid and also changed it to fluid. And once this was done, we hit generate to make sure it updates. For our mesh, we use all triangles method, making sure both bodies are selected. And we did a body sizing on the circular region around the diver with an element size of 0.02 meters and a hard behavior. Then we did an edge sizing of that circle with an element size of 0.02 meters and a hard behavior. Another edge sizing was done on the actual Skydiver with an element size of 0.01 meters and also a hard behavior, and we had to individually select all of the edges of the Skydiver to make sure it was completely represented. Lastly, we had a refinement of 2 on both of the phases to acquire a very fine and elegant mesh, as you can see here. Very refined along the edges, and this fine mesh will give much better results. For our name selections, the bottom of the rectangle was our inlet and the top was our outlet. Now for naming an interface out, you would have to hide the rotate body to correctly select the circle for interface out. Then you show the rotate body and hide the fluid body to name the interface in of the circle. And lastly, all 15 edges of the diver were selected to be named as Skydiver. Also, under the general details of the mesh, the element size was 0.5 meters. Once everything is named, make sure to update your mesh. Now we can go into setup. Here you can see our Fluent launcher settings with double precision, parallel, and 4 processes. In ANSYS Fluent, we changed our time to transient to represent our unsteady flow. Then our viscous model was a realizable K-epsilon model with an enhanced wall treatment. For our materials, we used air as the fluid with the standard air values. In our cell zone conditions, we changed the rotate to a mesh motion. Then for our rotation axis of origin, it was 0.5 meters in the x direction and negative 0.2 meters in the y direction. And these are the x and y coordinates of the center of the circle that we drew around the Skydiver. For our rotational velocity, we set it to negative 1 radians per second. Now we can go into our boundary conditions. Since terminal velocity is around 120 miles per hour, we converted this to meters per second and set our velocity magnitude to 53.6 meters per second. Our specification method was intensity and hydraulic diameter, and our hydraulic diameter was 50 meters because that was the length of the rectangle. For the outlet, we set it to intensity and hydraulic diameter with also the 50 meters diameter. For our solution methods, we made sure to change the turbulent kinetic energy and turbulent dissipation rate to second order upwind. Then for the residual monitors, we set all of them to 1e to the negative 6. Then we performed a hybrid initialization. Then we set our solution animations, making sure to record the time step. Then you have to select new object to create both the velocity and pressure contours. Make sure to unselect everything, select the velocity contour, then save and display and close. Then you make another animation for the pressure contour. Now we were ready to run our calculation. For our time step size, we set a size of 0.005 and 800 time steps. Then our iterations per time step was 30. Then we hit calculate. Then after 6 hours, our results were finally obtained. These are the contours of the velocity magnitude, where blue represents a low velocity and red represents a high velocity. This velocity ranged from 0 to about 82.5 meters per second. Then these were the contours of static pressure. Here blue represents an area of low pressure and red represents an area of high pressure. This pressure ranged from about negative 4,700 pascals to about positive 2,300 pascals. And in order to create the animations, we went into the results tab under animations, then clicked on solution animation playback and made sure to end the frame at 800. We unselected the stored view so that we could zoom into the image and get a better visual result. Then to write and record it, we selected MPEG and we wrote the animation sequence for velocity, which took about 15 minutes. Then we wrote the animation sequence for pressure, which took another 15 minutes. Once both animations were written, we check the file under which the project was saved. You open the file into DP0 FFF Fluent, and here you can find the animations for pressure and velocity. Here the pressure, we opened it with Window Media Player. Here you can see the static pressure as the Skydiver rotates. Through this animation we can see that the static pressure is highest where the air directly pushes against the Skydiver, since the air is rushing from the bottom upwards. Then for the velocity animation, scroll down a bit and open it the same way with Windows Media Player. In this animation, we see a lot more colors as the velocity changes, and we can see higher velocity along the edges of the Skydiver. And that pretty much covers our aerodynamic analysis of a Skydiver. Let me know if you guys have any questions in the comments, and hopefully you guys enjoyed.